So let's start with day 2. So yesterday we learned a lot about command line, the Morse code, Caesar ciphers, and all that. Today the lesson is actually going to be quite fun, right? We are going to be learning about how can we break these codes. So we learned about the Caesar cipher. We're going to be using 2 different methods to decrypt or to break the Caesar cipher. So if you don't have the key, you can still figure out what the message was using these methods. So there's 2 of them. One is called frequency analysis, and the other one is called brute force. Anybody has heard of any of these terms before? Is it all new to everyone? Cool. So we were going to work through them together, okay? And I'm going to introduce you to a different type of cipher. It's called the Vigenère cipher, and it is a lot more difficult to break. It is similar to the Caesar cipher, but it is a lot more difficult and more fun to work with, okay? And we're going to talk a little bit about security of these ciphers. And then we're going to end up with a few challenges, wrap up with a few challenges. So, okay, first one, Caesar cipher. How do we break the code if we don't know the key? So we're going to have these like scrambled letters, nothing makes sense, and we don't have the key. How do we work it out? So here for frequency analysis, the first method, we are going to be using the knowledge about the language. What do you mean by that, Mari? So here are a few examples. We're going to be looking for common words. So these words, they're called cribs. It's another term for them. And they're like words in English that we use all the time. So we have a few one-letter words like a, I, or sometimes we have apostrophe s after to indicate is, for example, or when it's someone's thing, we have the apostrophe s there as well. So we have 2-letter words that are very common. Is to. You can probably name a few as well. You have other examples in your minds, I'm sure. And there's 3-letter words like the, and, you, she. So just by knowing that the text is in English, and knowing that these letters are quite common, if you get a big enough text, you can probably figure out where those letters are, okay, or where those words are. So this is one of the things that we're going to be looking at. Another common thing in English is letter or words ending with the same letters, like ing. There's a lot of words that they end in ing, ed, eis, or or. You can probably think of other examples in your head as well. So we can use this knowledge and then also look for common letters. Remember that in the Morse code, we were saying that the most common letter in English, they are usually the simpler codes, maybe with 1 or 2 digits only, or 2 characters only for the Morse code. So those are very common letters in English. So if you see a pattern in a text that is all scrambled, that this letter keeps coming up all the time, and you know it's a Caesar cipher, you can guess that could be the letter E, because the letter E tends to appear a lot in English, okay? But there are a few considerations in relation to this, okay? So this is very language specific. So if it is a different language, E may not be the most popular or the most common letter in that language. So it won't work if it is a different language. And it is also dependent on knowing it also depends on the length of the message. If you get a message that there's only like 3 letters, literally, like, it's gonna be hard in a way, because you can't see these patterns. You don't know what exactly is written there, or if it's 5 letters. So this method may be difficult to work with, because this method, you're relying on analyzing the text to find trends, to find patterns in the text. If the text is small, you won't find much patterns there. Does that make sense? And then another thing to consider is that it may not, it is easier. So it is easier to break longer messages, as I said, and it may not work in short messages. Okay. This is going to become a lot clearer to you as we move on to the examples. Okay. So don't worry. And the second method is called brute force. So with brute force, using a Caesar cipher, that means that there's only 26 letters in the alphabet, right? So you can only, your key can only be a number from 1 to 26, right? So you can have if you really think about it, it's actually only 25 examples, because A can never be encrypted as A, because otherwise the text will be itself, right? Because B is going to be encrypted as B and C as C. That wouldn't make sense, right? So there is only 25 different possibilities for A to be equals B up until being equals Z. So that's 25 different possibilities. So if you do have time and it is a short text, what you could do, you could try every single one of the possibilities. You could have your cipher A equals B and try to decrypt the message using that. If you see that doesn't work, doesn't make sense, you go to C and then you try to decrypt the text with C. Does that make sense? Yeah, Evie? Have a question?
Well, I was just thinking that would also be kind of helpful, because then if you know that A is, just say, T,
Yeah.
then you know it's a shift of a certain amount of numbers. And when you've worked out what one letter is, and you know for sure, then you can just decrypt all the rest of it.
Yeah, exactly. When you know for sure, then you're set, because you know the key and you can decrypt the whole thing. But then sometimes for you to know for sure, it may take 3 or 4 letters, if that makes sense. Because then you put the 4 letters together, oh, this is a word. So there's good indication, and then you keep decrypting the whole message. But that's exactly that. You're right. Yeah, but one consideration with this method, it can be a little time consuming, because I mean, you're trying the 25 different possibilities, A equals A, B, C, D, E, all the way up to Z. So, but if the text is small, you can do it for sure, okay? So in the case where frequency analysis is a bit difficult, it wouldn't work because the text is too short, then we would go for brute force normally. So if that doesn't work, we go to brute force. Takes some time, but we'll get there. So yeah, with this, do you guys have the activity sheets with you for lesson 3? If you don't have, don't worry, you can still follow using the slides here, but if you do have it, just have on your side and we can work through these examples together, okay? Brilliant. So let's crack the codes. We have a few examples to work through here. So this is an example of an encrypted message that we do not have a key for. So we don't know what's the shift for the Caesar cipher. So any ideas which method could be suitable for us to use here? Would frequency analysis be useful, or should we just go for brute force? What do you think? Yeah, Evie?
Well, to be honest, I'd go with frequency analysis.
Yeah, why is that?
I just think that it looks simpler by a long shot.
Yeah, very good. Any other suggestions there, guys? Yeah, very good. So I would also go with frequency analysis, and the reason why I would choose frequency analysis here is because this is a long enough text, and we also know what's the length of each of the words, right? Because we have a space between the words. Does that make sense? So I know this is a 2-letter word. I know this is a 1-letter word. So I can use those the different text analysis for, and I know it's in English, so we can use that to try to figure this out. Okay, so great suggestion there. So how do we start this? What can we look for? So first thing, yeah, do you know, go for it, Alex. I saw you have your hand up.
Maybe look for like shorter words, because like say the PA, like this, it's not like it's gonna be like efficient or like a big long word. You know, it's only gonna be like quick and easy.
Yeah, it's gonna be like he or is, at, something like this. Exactly, that's great. So we're looking for short words, and the shorter, the better, right? And we know all the words in English, so we can figure this out, okay? So yeah, I have the cribs here, back here again, to kind of guide us and give us some ideas of what these letters could be. So the first step is for us to find the short letters. So we have here U, right? So or short words, I should say. So we have U, one letter words. We have PA, as Alex mentioned, and we also have UZ here as 2-letter words. And we also have 3-letter words there. So we can kind of like come up with some hypotheses and see if that works. For example, we could just say, we could say that U equals I, the letter or the word I, or U equals A, the word A, and test out in the other short words if that key would work. So how would we do this? We'd get our scissor ciphers and align in the outer circle U, or you can do the inner circle as well, U equals I. It's just gonna vary then where you're looking for it. But you could get your U and in the outer circle and align it with I. I'll just try to make it work here for me, while you guys can also try to make it work there for you. Yeah, so I have U here aligned with I. And then we can give it a try, see if that would work, okay? And then basically here we can decode the other letters, the shorter words. Fill out the code, well, let me see, fill out the piece in the entire text. Yeah, so decode letters in order. Fill out the decoded letter in the entire text. So say, if you see other U's in the text, you could put there an I and see if that would work, right? And then we can try the P and A, which are the first 2 there, right? So if we align U with I, and then we try to find P there, in the outer circle, P is down here, right? P would be D. Does that make sense? So our hypothesis is, if U equals what equals I, so we have the letter U equals what I, then we just leave the scissor cipher as is, and we try to decode P and A. So if U equals I, P equals D, and A equals O. Yeah, we have a question there, Manvik. Do you want to ask your question? You can unmute yourself if you want. Yeah, okay. You can ask later if you want. So P would be D, and A would be O. But yeah, D and O, that could work, right? D and O, it's a letter, it's a word in English, isn't it? Do. Yeah. So, okay. You're gonna see that like in step 3, you'll be able to guess the longer words at some stage that are so it's kind of similar to the hangman, where you're kind of like guessing what the letter is and seeing if that works out. So basically here we found out that if U equals Y, A equals 2, right? And then we can also look at UZ, because PA does work, we have 2. And what about UZ? What would UZ be? So if we go into UZ, we have U, where is U? U equals I, and Z equals N. I with N, N. So N is also a word in English. So we could keep trying, and also we can get all the P's and fill out these for them. We can fill out the U's as I in the entire message to make it work faster, if that makes sense. So you're not going letter by letter in the text and trying to figure it out all the time. If you figure out P once, you know it's D. This P here is also going to be D, and so on. Make sense? Yeah? Evie, do you have a question? Do you manage to make it work?
Well, I got the third line to work,
Cool.
but it doesn't make much sense, but it definitely is English language. Definitely.
Okay, what does it say?
It says mathematics, I assure.
Mathematics?
Yes.
I?
The really giant word.
Yeah, mathematics?
You
I?
see, I thought that if you was I, then you could go across with all the others.
Cool. Yeah, and then you got mathematics. So that makes
Yeah.
sense, yeah?
I did.
And then the first one here is 2. This is N. Yeah.
Mm-hmm.
Cool. So yeah, you can take your time to decode the whole message, but we found out it is English. It kind of makes sense once you have the whole text decrypted. Hopefully, it is a sentence that actually makes sense in everybody's head. Yeah. Cool. Does anybody have any questions? Did you find it easy to follow, or are you unsure about any bits of this, how to make it work? Yeah, you're good? Okay. So now there's another activity there. It is the same idea. So I'm just gonna work through the start of it with you guys. So then you can work it out later, all the other ones. Because once you know the key, you just keep your Caesar cipher as is, and you work through the other letters, okay? So again, here we're going to be using frequency analysis because it's going to make our life easier. We see we have a few short words. We don't have a one-letter word like in the last example, but we do have two-letter words, and we have 1, 2, 3-letter word that appears twice. So with this one here, we can use the same idea. We can try matching H and more with is or to do, and see would that work for this example, okay? And then eventually you're going to see, oh, this word means this, okay? Make sense to everyone? Yeah, I can see you're working through your activity sheets, which is great. And the third one, I'd like you to just have a look here and try to figure this out together, because there is something that is different here. What is different about the third one? Yeah, Alex?
There's no spaces.
There's no spaces, so we're in trouble. What does that mean? Can we use frequency analysis here? Yeah, Manuel?
No, because we would have to use brute force since there's no short words and there's no spaces. There's only
Yeah.
long words. So
Yeah,
we'd have to use brute force.
true. Can you see any patterns or anything that we could use as an indication that it might be the end of a letter or anything like that in the text? Is there anything different from a letter there that we could use?
Sometimes there could be commas and yeah.
Yeah, very good. That's great, Manuel. So here we have an apostrophe, right? So we could use that information to our advantage, okay? So in breaking codes, we're always trying to find patterns. We are always trying to extract some information from it. And like this is one of the really useful information that I see here, the apostrophe. Another thing that we could potentially look for is a letter that keeps repeating itself, it could be the letter E, because we know E appears a lot in English, for example, or it could be A, or letters like this, vowels that appears a lot. So this is also something that we could look for. Another thing that we can look for here is to know that sometimes in English there's letters that appear twice, like double L's, like it appears in a couple of words. Double P's, it appears in a couple of words, or double C's. So when we see letters together that are the same, we can possibly make assumptions like this. So even though we're guessing, we're making a more intelligent guess rather than just like guessing at random. We're trying to find patterns. Yeah, Alex?
And as well, say you saw like a double, like what you call it, like a double letter right in here, right? Because there's no spaces. Normally a double letter is sometimes, a lot of the time, at the end of the word, so you might know. I mean, sometimes it can be in the middle, but sometimes it's
Yeah, sometimes it's at the end. Exactly, that's really good. So we're looking for these patterns from knowing the language. We can see some patterns and use that information to help us with this. But in this example here, I'll walk you through like how I would work this out, knowing that this is an apostrophe. Okay, so let's see how would that work. So yeah, I just have a few things here. So there's no spaces, as you guys said. What does that mean? It means that we can't use the common words, the cribs that we were looking for, the short words, because we don't know the length of the words. So let's review our options here. We were talking about frequency analysis, and in frequency analysis, the first thing that we talked about was the common words, the short words. And we also talked about common sets of letters. So if you see, if it's a long enough text and you see that these three letters keep repeating themselves, it could be the ending to a word like ing or ed. We talked about the common letters like I or E. And here, these are informations that we can, or these are pieces of information that we can use. So we have the apostrophe there. So we can make a hypothesis that after the apostrophe, there's going to be an or and an E, like they are, you know, they are, or an E, or I've, the V and E, or N and T. Does that make sense to everyone? Yeah, so we can use these hypotheses to make better guesses. Okay, so I came up with a hypothesis here. My first hypothesis, that the NB here is actually NT, like aren't, yeah? But that would mean that N equals N. And remember when we were talking about it, that if you encode the letter as itself, like A as A and N as N, you're going to end up with the same text. You're not going to be doing any encryption, actually. Yeah. So that wouldn't work. That wouldn't be possible. It wouldn't be possible in this case, knowing that it is a Caesar cipher. Yeah. Another hypothesis that I have here is that N apostrophe B actually is the same as I apostrophe M. So that would mean that N equals I. So if I go in, if I take my Caesar cipher and align the letter I or the letter N with I will end up with this. So, ooh, there we go, N and I there together. What would be B then? So if we go to B, B would be W, it seems. So that wouldn't work, yeah, because I apostrophe W doesn't really mean anything. It's not a thing in English. So we can come up with a different hypothesis here. What about apostrophe BO is apostrophe RE? Would that work? So if I align B with O, or B with R, I should say. So I have them here together, my B and the R. Let's have a look at E. E and R. E would be U. Is that, or is that, no, sorry, O, we're looking for O. O down here would be E. Yeah, you can work out the same thing there. So if you just align your B with OR up here, when you go to the other side, you are going to see that O aligns with the E. It's a bit off my thing here, but promise you. So B is E. So this kind of looks good, doesn't it? Because if B equals R, O equals E, then this is like they are, like apostrophe ER. So that could work. So what would we do next? We'd come here to the first letters to see would that work. And then when it came to the first letters and I decrypted them using the same Caesar cipher without moving anything, I saw that it wouldn't really work because V, J, and W would just turn into FTJ. That doesn't make sense. It's not even the beginning of a word or anything. So then I came up with a third hypothesis. And then in this hypothesis here was that B equals V. So if I get my Caesar cipher again, and align B with V, let's see what O aligns with. So B is aligned with V. If I go down to O, O aligns with I, okay? And that is not possible. So then we can go to hypothesis 4. What about B is S? And then you go again. So you can see that even though we're making decisions that are based on frequency analysis and the knowledge of the English, it can be a bit difficult to come up with this. So if B equals S, let's see the first 3 letters. V, J, and W would be man. So that kind of makes sense. So V, J, and then W equals men. Okay, so yeah, this looks very promising, and that's how you would work through it. This is why I wanted to do this one with you guys, because I guess it can be a bit more, I wouldn't say it's more difficult, but it's more tedious. It takes more tries to get it right. Does that make sense? So we came up with 5 or 6 hypotheses, and that's how we actually got to the answer, yeah? While for the other ones, it was a lot simpler. Do you agree with that? Was it simpler, the other ones? Yeah? Very good, but now you know the shift for this one. What's the shift? If you're aligning B with S, which is the hypothesis that proved to be true, then A equals OR, okay? So then you can use that as your shift. So if you want to take a note there so you remember for when you're decrypting the message, then you can, having the key is going to be make it a lot easier. Cool. Do we have any questions on this before we wrap up the breaking codes part? See if we have. Okay, no questions. Did you guys get it all? Was it easy or was it more a bit challenging but got there? Easy? Okay, I see some thumbs up for easy. It's great. Oh, you guys are so smart. Yeah, I found that it could, yeah. For me, it took some time, but I got there. I got there. Practice makes perfect. Good stuff. So now I want to congratulate you guys on learning all about Caesar ciphers. So we learned about how to encode the Caesar using Caesar ciphers. We learned how to decode text. And not only that, we learned how to break it as well. So even though you don't have the key, you know how to break it using 2 different methods even. Yeah. So that's really, really great. Congratulations, guys. Now we are going to be talking about another cipher, which is similar to the Caesar cipher, but it is a lot more secure. And you're going to find this a very clever move, I'm sure. So with the Vigenère cipher, it is a method as well for encrypting messages by combining different Caesar ciphers in a secret keyword letter. So instead of just having a shift, a number, or A equals something, This time you're going to have a keyword as the key. It's not going to be a number or a letter equals another letter, okay? And it uses the 26 possible Caesar ciphers to encode messages. And then in this case here, A can actually be A, and that's fine. And you're gonna learn why. It's fine to sometimes have A equals A, which wouldn't make sense in a normal Caesar cipher. So the length of the keyword here is going to determine the number of different encryptions that are going to be applied to the plain text. So an example here, if our keyword were code, for example, we'd be encrypting our message with 4 different Caesar ciphers. We would be encrypting it with A equals C first, and then after we'd do A equals O, and then A equals D, and then A equals C. So if we can use the Caesar cipher, this one here, to encode it, but then we'd be moving it around, if that makes sense. So first we'd start off by aligning A with C, and then we'd encode a letter, okay? So I have my A, where is it? My A aligned with C, and then we'd encode the letter. And then we'd need to move it. We'd go A equals O. A equals O. Don't know where A is. I didn't align it correctly. There we go. So A equals O, and do it and do the not another letter, and then do it again. So it can get a bit tedious if you're doing it using the Caesar cipher, and that's why we have a different page there for you guys for the Vigenère cipher. This one here, yeah, because this is going to make our life a lot easier to encode these lists. So the Vigenère cipher is a polyalphabetic cipher, while the Caesar cipher is monoalphabetic. What does that mean? Yeah, Omar, I see you have your hand up. Do you have a question? Okay, yeah. Cool. So do you know what mono stands for? Anybody has any idea? Have you heard it? Yeah, Evie?
So mono means like one.
One.
So it's like one alphabet, kind of.
Yeah, that's great. Leonardo, would you know about poly? I see you have your hand up. Maybe you know it. Poly.
I don't know what poly is. I just know what a mono is.
Yeah. So one good indication, like knowing that mono is kind of one, basically poly is more than one. Okay. So the Caesar cipher is monoalphabetic. Why? Because we just choose one key, like A equals 3 or A equals C, which is the same. And then we go with that, right? Or A equals 3. Yeah, A equals 3 would be A, you'd go A, B, C. Is it? Let me see. So A equals 3, we'd land on D, because we'd go 1, A equals B, 2, A equals C, and then 3, A equals D. And we just use this as is. We only move the Caesar cipher once, and then we use this to decrypt the message. But with the Vigenère cipher, because it's polyalphabetic, we're going to be using different combinations. We're not going to use only one, okay? And that's how it is different, like what I showed you with the code, the example code. So one key thing here, why is this so much more secure? Because with polyalphabetic cipher, the same character can also be encrypted in different ways. So it's not like the letter A is always going to be encrypted as B, as in our example here, yeah? So the letter A, when it appears in the text, it may appear as E once, or D, or A, it can be anything, yeah? So that makes it a lot more difficult. So it also means that the same plain text letter may appear encoded as different letters in the ciphertext, as I was saying. Does that make sense? Yeah, Evie?
So with the this is just a random question. With the Caesar cipher,
Yeah.
A cannot be encoded as A, B cannot be encoded with B.
Yeah,
Because this is polyalphabetic, does that change or is it the same?
it does change. So sometimes A can be encoded as A, and that's fine because it's going to be scrambled in there, and you probably won't even notice, you can't use that information to in your advantage to break the codes. Yeah, that's a great point there. So like with the example that we had, if the keyword was code, and if we were to encrypt A would be encrypted as C first, and then A would be encrypted as O, and then A would be encrypted as D, and A would be encrypted as D. So you can see that the plain text A, suppose this is what we want to send someone, would be actually be encoded as the ciphertext code. So how could you even tell that code would actually be 4 A's altogether, So it's a lot more difficult to break. So this is going to be affecting the frequency analysis that we used, because now we can't assume that the same letters are going to be encoded as the same letter later on. It is going to change. So it makes it a lot harder to break the Vigenère code because we can't use frequency analysis. Yeah. So let's see how we can use the Vigenère cipher to have more secure encryption. Okay, so one key thing here is that the columns here, so the columns A, B, C, D, E, and so on, I'll just use it here actually. These columns here, they're going to be the plain text message, okay? So whenever you want to encrypt A, you'd be looking up here, A, okay? So, and the row is going to be the letter in the keyword. So remember our keyword before was code. So we'd be looking, for example, for the C here first, and then we'd be looking for the O here, okay? So this is just something to keep in mind. The columns are for the plain message and the rows are for the keywords. So the ciphertext is going to be at the intersection of the plain message here and the keyword. So say if the plain message is C and the keyword is K, my encrypted text is going to be M. So I'm just going to substitute C for M. Make sense? Yeah, kind of? I'll just keep an eye on the time here. We have about 10 minutes. I think we can do it. So yeah, let's see how we would encode the plain text hello with the keyword code using the Vigenère cipher, okay? So as I said, we have the plain text there, hello, and we have the keyword. So the keyword is going to repeat itself by the length of the letter. So we start with code, and then we would be rewriting code here if there were more letters, if that makes sense, yeah? So if there is a space, you can just leave the space B, and then the next letter would be the O, yeah? So, okay, starting with H, remember that I was telling you that we need to find the plain text in the columns here, yeah? So we'd identify where H is here, and then we would go into the rows here and find where C is. So C is up here. So we have our plain text, keyword. Now the ciphertext that we are going to use is J. So I'm going to encrypt H, S, J. Is everybody following? Is that easy enough to see how it works? Yeah? Okay, good, great. I see some nodding there, which is good. Okay, thumbs up for Aiden. Thank you, Aiden. Good, so you're following, that's great. Next, if we were to do it for E, we'd find E in the top column, then find O as the keyword, and then in the intersection, we have S. Yeah, does anybody want to try L? Can I have a volunteer? Let's see. Yeah, Jason, do you want to go for it?
L, you go down to D, I think.
Yeah, L, you go down to D, and then
And
the
then there's an intersection between O.
yes, excellent. L, you go down to D, and intersection is O. Perfect. Now, this is where it is really different from the Caesar cipher. Remember, in the Caesar cipher, every time you had two letters that were the same, you'd encrypt them as the same. So here we also have another L, but it's going to be encrypted differently. Yeah. So Manvik, do you want to give it a try? If you were to encrypt the L now using E as the keyword, the letter in the keyword.
Okay. You. So in the column, so the one that's going that way, you find L.
Excellent. We have L here.
I mean, and then the one that's going down there, you have to find E.
Excellent. So we have E down here. And in the
Yeah.
intersection, what do we have? The letter
E.
E. Excellent. So you can see how different it is from the Caesar cipher.
Yeah.
L and L was encrypted as O and P.
Yeah,
Do you
but
wanna give it-
I have something else to say. D and E is next to each other. O and P are next to each other as well.
Yeah, exactly. Because D and E are next to each other. O and P is also next to each other. Excellent. That's a good observation there. Awesome. Thank you. Thank you for helping us. Anybody wants to give it a try with the last one with O? Do you want to go first, Manuel?
So you would start at O and you would end at C, which
Yeah,
would be Q.
you. Excellent. Awesome. So we have it. Well done. We encrypted the plain text hello using the keyword code using our Vigenère cipher. And this is what the cipher text looks like. I'm sure nobody would tell this actually means hello without having that keyword. So now we're just going to work our way back for you guys to see how it works. It's a little different, but not too different. And then we wrap up this lesson. Have a question, Evie?
I was just wondering, I can see now why it would be harder to break because people are immediately, when they think hello, they are looking for two identical letters next to each other.
Yes, exactly. That's a very good observation. And it is not identical in the ciphertext. So yeah, we can't really use that aspect of frequency analysis here. Cool. Let's try decrypting the message and then we go for a break. Okay, so now we're back with our ciphertext that we know means hello, but how do we work it out? How do we work out the way back? So it is similar to what we were doing before in the columns. The columns is where you're going to find the plain text, remember? So the actual message is always in the columns and the keyword is always in the rows. Okay, so how would we work this out? Basically, we would work out by finding the letter in the keyword. So C is the first letter in the keyword, and we would work our way down up until we find the ciphertext, which is J in this case. And then now we look up what's in the columns. That's where the plain text is. So the plain text is going to be H, because when we go down the keyword, the letter C from the keyword up until the letter J from the ciphertext, we go to the column H. Does that make sense? I'll do another one and then I'll get some volunteers to help. So S, I'd go down to S here. Oh, sorry. For deciphering S, we need to use the keyword O. So we'd go down to O instead. And we'd go here up until S. So there we have S. And now we need to look up which column is that. So that's column E. And that's how we get our E back. Okay. Can I have a volunteer for the O? Manuel? Yeah, and then Manvik goes next.
So basically you would start at D and you would and L. Oh, wait, no. Wait.
You'd go
You
down.
you would go to O, and
Yes.
then above there would be an L. So it'd be an L.
Yeah, thank you. That's great. Do you wanna go for it, Mangvik? I saw you had your hand up before. Yeah. You can unmute yourself if you want. Then we have the L there. How would we decrypt P using keyword E? And maybe he's having trouble with his audio. Do you want to try it, Jason?
No, no, wait. I was speaking with
Oh,
my mic off. Sorry about that.
No problem. You can go for it.
Okay, so find the E in the row that goes down.
Yes.
I zoom into there. So there's a P there. If I zoom in
Excellent.
to the P and then I zoom into that row and then come back, I will see an L there.
Yes. Great. Well done. Well done.
So the next one is another L.
Yes, it's another L. Let's work that out as well. Jason, do you want to help us? And then Evie does the last one.
So you go down to P, and then you go across until you reach D, I think.
Oh, actually, you go down the keyword, remember?
Oh yeah. Sorry, you go down to D, and then you find. I mean E.
E. Yes, that's
is
right.
C.
You go down to E.
Uh,
And then
E, and then you go to P,
mm-hmm.
and then you go up to that column, and it's an L.
L again. Excellent. And then Evie, do you want to do the keyword, the key letter C and ciphertext is Q?
So you'd start at C on the vertical row,
Yeah, C.
and then you'd go across until you got to Q. And when
Excellent.
you reach Q, you go up, and then you're at O.
Oh, excellent. Yeah, you got it, guys. So we got our plain text hello back. And this is how you decrypt using, once you know the keyword for the text. So let's just wrap up with a few questions to get us thinking about everything that we learned here. So which method do you think is harder to break? The Morse code, the Caesar cipher, or the Vigenère cipher? Yeah, do you wanna give us our guess, Jason?
The Vigenère cipher.
Yeah, and why do you think so?
Because there's like if there's a double letter in the word, it could be different. The letters could be different, and you would never know. Like in hello, L's were O and P, so it'd be really hard to know.
Exactly. And you also don't know how many letters there are in the keyword. Because imagine if the keyword is just 2 letters, then you're going to be encrypting the message only using 2 different Caesar ciphers, if that makes sense. You'd always be going into the same rows here, the same 2 rows. But if the keyword has like 7 letters, you're going to be using 7 different Caesar ciphers or 7 different rows here to encrypt the same message. So it gets a lot more difficult to decrypt or to even break the code. Leonardo, do you have any other comments on this?
I think the Vigenère cipher is the trickiest one to solve because like you can't solve it if you don't know the keyword.
Yeah, it is. It is actually kind of possible if you don't know the keyword, but it is so difficult. Yeah. So yeah, and you really need a very, very long text to be able to see any patterns there. But yeah, it's nearly impossible. Like for us to do it by hand, nearly impossible. Maybe if you have a computer with really, really smart algorithms there, it will figure it out, but it will take time. Yeah, that's really good. So what factors make a Caesar cipher hard or a cipher harder to break? Is it, do you remember what the key space was? Maybe I didn't touch on that so much. So the key space is basically in how many different ways you can encrypt the message. Okay, so for the Morse code, A would always be the same code, remember, would be always be, or E, I remember it was a dash or a dot, because that was the easiest one. So the letter will always appear the same. It never changes. That's the Morse code. For the Caesar cipher, it would change sometimes. So if the key was A, or if the key was B, A equals B, B would appear as B, or A would appear as B. And if the keyword was a different one, it would appear differently. But there were 25 different possibilities. Remember, we were discussing this. A equals B up until A equals Z. And that's all. And so the key space there would be 25. Well, because you have 25 different possibilities, different ways of encrypting that whole message. But for the Vigenère cipher, you can use all the 25 or 26, 25 different or 26 different letters in the alphabet to encrypt it. And you can use it different times in different orders. So the key space, the number of different possibilities there is a lot bigger, okay? So this is one of the main factors there that I'd like to kind of highlight for you. For the Morse code, it's one possibility. You know, you have the chart, you know what that letter is going to be. Caesar cipher, there's 25 different possibilities. But for the Vigenère cipher, there's a lot more, okay? So the factor that makes the cipher harder to break is the key space. The number of shifts in the Caesar cipher doesn't make it harder. It just means that you need to shift there a little bit more, but it doesn't make it harder, okay? And which messages are easier to crack using frequency analysis? Is it a longer message or a shorter message? So a lot of words or just 2 words, which are easier to break? Yeah, Richard?
Two words.
I would say this can be like, if it is like 1 or 2 words, or I'd say up to 5, like it's not so difficult, because then you can use brute force and it's quite easy to use brute force in that case. But if it is a longer text, then it is good because you can crack it using frequency analysis, as we were doing. So then there's only so many possibilities for 1 letter in English, or 1 letter word in English. So there's only like maybe 5 or 6, I don't know. So it can be quite easy. So I would say that longer messages could be easier to crack sometimes, because you can use that information from the language to decrypt it, okay? But shorter messages, as you said, like if there's only 2, that's pretty easy, yeah? But you know, like it's gonna be hard for you to know, did you get it right, you know? Because it can be the case. I think we had the case there where we could decrypt it as VE, which would make sense, like I've, and we could decrypt the same thing as BE, using a different combination or something like this, or I, something like this, and it would work as well. So we just need to be mindful of that. But yeah, let's get to our break.